Swayam Prabha. Digital India. Educated India.
Welcome to the NPTEL course on building energy systems and auditing. In the module number 6, we are discussing the life cycle analysis and the energy audit. In that, in the lecture number 28, we will now discuss the building life cycle analysis. So, in this particular lecture, we will see the other two type of the energy, that is the operating energy and the demolition energy, and we will see the distribution of the life cycle energy and its analysis. So, if you see the stages of the material life cycle, so we can actually see that a material has to be manufactured, and before the manufactured it has to, we should get some raw material. In any case, maybe it is for the brick, it is for the steel, it is for the cement, glass, every material you require raw material extortion, and then this also required some energy. You require energy for the manufacturing process, and probably that is why the metals are more having more energy density, embedded energy density per meter cube, or the per kg of the metals will definitely has more energy. Then after the manufacturing is being done, so we transport that material to various places, and then from the various places to various sites depending upon our demand or so. We use it, we retail it, we use it for the total lifespan, and then we go for the disposal after a certain time. Maybe you have to demolish the building, or even may not be demolished, but some the material has to be changed. So, these 5 points, or you may say those are kind of the prominent the locations or the prominent points of a building life cycle or the material life cycle. So, in that, if I say it is if it is cyclic kind of a thing, so I can say it is the raw material, manufacturing, then the transport, then the use, and the waste. So, in this, if I now linearly if I see, so it is a production from the raw, then it is the industrial processing and the manufacturing process, then we transport it and then we can use it, and there is the end of life. So, if I say this, the raw is first box, the manufacturing is the second box, the transportation may be the major transportation will be happening after the manufacturing and the use. The third box is your use, and the waste and recycle may be the fourth one, the end of life. Now, there are some boundary conditions. So, the system boundary, we can say that from where to where we can see this particular energy. So, sometimes we can see that it is cradle to grave. What is cradle to grave? Cradle is the start point, or the first one, that is 1 to 5, stage number 1 to 5, because stage number 1 to 5 we have discussed over here. So, it is raw material to the waste. So, it is waste means it is grave. So, it is end of the life, and cradle is the newborn baby in a cradle. So, it is the raw material. So, it is a full lifespan of the material. So, from how much energy you are induced or incorporated in a particular material from the cradle to grave is the total life cycle energy. But sometimes we may go little bit of other way, see the cradle to gate. So, what we have discussed in the last discussion. Last lecture that we discussed the embodied energy of a building, a multi-storied the apartment building. We actually considered the cradle to gate kind of a scenario. The assessment is produced from the stage 1 to stage 2. So, most of the raw material and manufacturing, and this is gate. Which is the gate? That is the suppose the gate of the industry, just it is leaving from the gate of the industry. So, the maximum energy that was actually embedded into a material is the raw material excursion and the process production and all. And then there is a definitive transportation, there are some construction, maybe welding and this and that is there, and then finally, the end of the life or so, but those are not that much with compared to the first two stage. Sometimes people say it is the cradle to gate, that will be enough to assess my energy. So, the cradle to grave, or this is the cradle to gate. The last one is little bit sustainable. So, it is cradle to cradle. So, what is cradle to cradle? That we will not the fifth one, the waste and the recycling, that will be going to be no more. I mean, there is no end or no death of the particular material, the end of life. We will recycle it, the waste recycle we will do. So, what we will do? We will skip the 5, or maybe we may say the 5 and a 1, the second one, not the first one. The first one is the manufacturing raw material, raw material excursion, and the second after first loop, the 5 goes in the first. So, in the horizontal flow diagram, it starts from the cradle, a material. At the end of its life, again I try to manufacture it from that material as a raw material. So, nowadays you all know that in the sustainable development we need to do that, and we need to do, even we are thinking of using the demolition material from the building, and we used to do that for the new material, sorry, not new material, for the recycled material we use for the construction. So, how much we can do, that is really challenge, because people are working in that area. So, but some of the metal items, maybe after the end of the life we can actually reuse it, plastic things we can reuse it. Only thing is that we may say that the whole 100% of the material which is actually came to the grave, we may not use as 100% as a second cradle stage, because there will be some kind of the change of the property of the material, or maybe there is some kind of the damage which cannot actually take care of that or so. So, anyway, even if we cannot use the whole 100% of the material, we can actually think of using the maximize the amount of the use of, or recycling the material, which actually going to beneficial. So, the world is thinking in this way, and then we have to also think, the civil engineers, architects, building consultant has to think that, and we need little bit of research in that area, we need little bit of the application testing, some demo house or something like that. So, that it can be fulfill some of the technical demand, technical requirement in the future. Technical requirement I mean to say is that anything you do, you need to have a kind of justification from the building code. So, if you design a building, if you design a structural elements of the building like beam, column, whatever, you have to actually follow some code, the IS code, IS 456 or something like that we have to follow. So, similarly, if you use the recycled, the aggregate or recycled steel or maybe anything with a new part, of course, I mean cement may be the new or whatever, then you need to have some justification from the technical point of view. So, you need a code. So, to develop a code, new code for the recycling of concrete or so, you need research. So, it will require some time to that kind of thing, but before we actually design for the large stock of housings also or the buildings, we can actually think of doing some kind of the demo housing or some kind of that. So, the awareness, people awareness and all these things are there. So, that is why I have introduced these things. So, there are three things: the cradle to grave, cradle to gate, and the cradle to cradle. So, last two lectures we have mostly focused upon the embodied energy. If you remember, there are two types of embodied energy we discussed, one is the initial and one is the recurring. So, now next is the operating energy. As you understand that a building will take maybe 2 years to construct and it will stay for 50, 60, 70, 80 years for its life, operating life, and then maybe again it required maybe 2 months or 3 months for demolition if the life is over. So, the maximum part of the building life cycle is actually in the operating stage, and we need to find out the operating energy of the building, and it is a very simple conceptual equation. I must say it is look very simple, but it is not so simple. We are already started discussing on that from the very first chapter, building physics and all the heat gains and all those kind of a thing. We will also discuss in the next week, that is in the week number 7, how to calculate the operating energy or estimate the operating energy. After this particular slide or this particular lecture, the next lecture on the 29th and 30th lecture, we will see that what is the way to find out this operating energy of a building which is running conditions or so. So, in this particular paper which is by Ramesh et al., it has given that the operation energy is the annual operating energy, which is EOA and multiplied by the life of the building. But this EOA, that is the annual operating energy of the building, is not very static, it fluctuate. If I say that only one day I will calculate and then I multiply with the running number of days or so, it probably not going to be the same. So, you need some kind of investigations or so, it is not going to be the same whatever the energy I am going to, annual energy coming in the year 2024 is whatever year 2030 will be little bit more or less. So, it has a little bit hazy area, but still we have to do, we have to find out that particular the footprint of the yearly footprint of the energy. So, that is why I say that this equation looks very easy or very slick, but it is not so easy to do that. And then finally, it is again conceptual that the demolition energy is the summation of the energy required for the demolition, energy required for the destruction of the building, and the transportation of those material, waste material from the site. So, now let us go to the overall life cycle understanding, the proportion of the life cycle or so. So, as I told that the initial 2-3 years I will be spending for construction of the building. So, if I spend 2 to 3 years or maybe little less than that for the construction, I require some kind of embodied emissions or so. So, the y axis is amount, if I say this y axis is the total amount of energy. So, initial embodied energy is not so high, but the intensity of the initial embodied energy is high. The intensity means within 2 to 3 years, the per year the amount of energy I am going to spend for the building is high. So, this rectangle is not the greatest rectangle out of the 4, but this rectangle is the inverted rectangle. So, the footprint of the rectangle per year is very high. Is it clear? It has been very well given this in this particular the paper, Ibn Muhammadah. In that paper, this has been wonderfully clarified and suggested this particular diagram to be incorporated in the the process of the estimating the life cycle energy. If you see the next smaller this one, the rectangle, the lower rectangle, which is a recurring embodied energy. Recurring will occur after the construction, that is why it is after the yellow rectangle. So, it starts from after 3 years and continue till 40 to 60 years, the total life period of the building. So, this is the recurring embodied energy. Total footprint is also not so high, but it is elongated till the end or so. And then this green part, the maximum part is the operating energy, and operating the emissions also. So, in that if you see what is written here, it is because of the energy uses, it is accumulated over time, it is due to the mainly due to the operation and the occupant, it is written, but embodied energy does not depend upon the occupant. It is the building primary energy for the material used, and this is for the occupant, the operational energy green one, that pattern of the energy use, how I am using the energy, what is the building, what is the type of the building, based on that what is the function of the building. So, this green rectangle is the total impact of the operating energy over the span of the building life of 40 to 60 years. So, that is the another. The last one is the demolition energy. It is shown the demolition footprint is also quite high, maybe high or low depending upon the how much is your building height and building total the footprint areas or so. So, from that point of view, but this particular diagram is a very wonderful diagram that depict the proportion, the intensity and the variation and the length of the different type of energy. Next is the another, and this particular also, I mean this particular paper, the Ibn Muhammad's paper also suggested lot of other things. The first one, let us discuss the right hand side graph, where it has suggested that the operational energy is quite high and almost about 80%. If you see the y axis gives 0 to 100 total the life cycle, out of that this triangle, the area of the triangle or whatever may be the total amount is the 80%. Yes, and this the embodied includes the both the embodied the recurring and the initial, which is about 20% or so. So, this is the most of the nature of the embodied versus the operational, but if you contribute little bit more in the embodied, your operational may sometimes come down. We will discuss in it will be the change of the variation of the embodied versus the operational in the when you go to the next week for the retrofitting chapters. In the left hand side graph, which again has been proposed by this paper, has 1, 2, 3, 4, 5 lines. If you see the first, the lower one is the total, the first lower one is the initial embodied energy, which is a constant kind of a scenario, and then the recurring embodied energy is a green one. This is the initial, this is the recurring, and this is some of the data that they have used in that particular paper. The second one, the orange one is your total embodied energy. That means, this if you add this one, this the dark blue and the green, if you add these two, you will get this. Now, we are left with one more. They have not definitely taken the demolition energy, demoliting energy or so. They have taken the operating energy, which is the red color line, the operating energy, which is this. This is OE. So, if you see the total energy is again this is I may say that the total embodied TEE, total embodied energy plus the operating energy gives you the total the energy whatever total energy, which is a black line again. And now, if you see the total embodied energy, which is the addition of the recurring and the initial, and if you see the operating energy, these two are the sloping line, but the TEE, the total embodied energy, slopes a little less because it is not so intensified, it is less 20% of it. So, it is less, but the operating energy stiffness is higher than the inclination is higher than the total embodied energy inclination. So, at certain after certain years it will going to cross the imprint or the amount of the total energy embodied energy, the operational energy will going to cross, and that is called the overtaking time. So, based on this particular fundamental concept, let us discuss this problem. So, this problem is already explained in the lecture number 26. I have mentioned, you can go back and you see, if you remember, we have discussed two parts in that lecture. One, we have with this data we have found out the EEI, that is the embodied energy, initial embodied energy, which is something like 5,83,000 something, and also in that particular problem we also discussed or calculated the recurring energy, which is 55,000 something. But if you remember, if you see that it has the 50 years of life period and 5 years of the material life. So, there is a 9 times I have to repeat the repair or the renovation, because it is 50 minus 5 minus 1. So, 1 minus because it is already taken into the time of the construction or so. So, this 9 time total amount of energy is 55,462.5. So, I can divide that, but by 9, this 55,462, and that will be the division, that whatever comes after the divisions, the quotient of the division will be the each time how much after 5 years or so, each time how much recurring energy I am requiring. So, the first let us draw a graph on the time versus energy scale. So, the first one is the static, which is your 5,83,250. Which one is this? This, which is a flat, right? And then the ER is 55,462, and that if I divide by 9, because 9 times I have to do, I have to do is recurring is 9 times, and 9 times after 5 years of each. So, each time I have to actually pay 6,162.5 the megajoule energy for 5 times. So, each one of this is your 6162.5, each steps, those small steps. And finally, after 50 years you have total of this much, 55,462. So, what we can do? We can do that instead of going these steps or whatever, we can it is the EI plus ER is this much if you add up. So, what we can do? We can draw a sloping line instead of the step line or whatever. We can draw a sloping line. Sloping line will give almost the same character of the energy footprint of the recurring, and the slope will be, I will divide the whatever 55,462.5 by 50, the amount, the number of years or so. So, I may say that per year, this is per year of out of this 50 year per year ER. So, it is maybe say that this is small ER, the per year this much amount of the recurring energy is requiring megajoule. per year. Okay. So, that is that is defining by this dotted line. So, what we do is that, so if I again little bit go back, so I can say that this one is actually your, it starts from and this goes like this, something like this, and this is like this. Okay. So, finally, it look like this. I have removed this the steps. So, this is the recurring. Now, suppose in a certain case, this is the sloping line which shows the recurring, and the next line is your total EI line or so. So, finally, this is your EI plus ER line, because I am adding each time. So, this is your EI, the initial and the recurring together. So, I can see it is the total, this is the total EE line or so, and this is my operating, the slope of operating I have taken OE. So, the OE, the smaller letters is your maybe some kilowatt hour per year or megajoule per year, some unit, and similarly this is also can be written as the kilowatt hour per year or megajoule per year or so. So, that means this is the point. Okay. Before that, so if I say that see the building is running after some time, maybe after some time, maybe after 30 years, 30 is too much, 20 years. If you do not do any kind of maintenance or so, due to the lack of maintenance, the operating energy will be very high. It will not going to the way it was there in the first 20 years or so. There may be some damage in the roof, there may be some kind of damage in the some insulation part, there may be some damage in the roof chhajjas or so. So, it will, or maybe the window panes are not giving you, it's maybe it has some kind of the insulations or maybe some kind of the black films or these are not maybe working. There will be some gaps in the window frames or so that leaks the, or it is going to infiltrate the outside air or so. So, without that kind of the proper maintenance, regular maintenance, if you do not do, your operating energy line will go up. But if you do maintenance, it can brought down or at least maintain the same slope, initial slope, but if you do some kind of a energy retrofit. So, if I do the energy retrofitting, after some 20 years you feel that no, you have to do something that I can reduce the energy footprint or energy operating energy. So, yes, you can do that. We will discuss that one in the next week. The 2 lectures will be there on the energy retrofitting. So, we can do that also. So, next one, let us see that again, so here what we understand is that you need to do some kind of maintenance, minimum maintenance, just to lower down that energy and going with the blue the green line also. We may not want to reduce it, but if I do some kind of retrofitting, because new materials may be coming after 20 years or so, which I have not thought of today's design, I can introduce that one in the after 20 years, and then the operating energy will be go down. So, in this we can actually say that after certain time, this green line is going to overtake this dotted line. Okay, that is called the overtaking time, and the overtaking time can be calculated by this formula. I have taken that this OE into OT, OT is overtaking time, OE is the operating energy intensity in kilowatt hour per year, and the EER is the the recurring embodied energy intensity in kilowatt per year, overtaking time in year, and EEI is the embodied energy. So, if you see that actually its overtaking means what? At this particular point, the total amount of green is equal to the total amount of red dotted portions of the triangle and the below portion. The below portion is my EEI, capital EEI, and this portion is my EER into this x or y. I have written as y, that means this is my y, or sorry, not y, OT, sorry, it is OT, overtaking time. This is the one part, and the green one is the OT, OE. So, that part is the OE into the OT. So, this must be equal to this plus this, plus this. So, finally, I got. So, if I reduce the OE, if you reduce the OE, definitely the OT will be higher. So, you will cross it afterwards, and that is good. I mean, that is good, because otherwise you cross it afterwards means your green slope is little less, and that is definitely good. So, I have taken some problem, a building having 650 meter square of the built up area, lifespan of the building is 80 years, the life cycle related data are given. Embodied energy initially is almost 1700 kilowatt per hour per meter square, recurring embodied energy is 5500 kilowatt per year. So, this is your EER, this is your EEI. Of course, you have to calculate, which will multiply with the building built up area, and this is OE. So, based on that you can calculate the what is your EEI, this is your recurring embodied energy for 80 years, and this is your operating energy. So, it is a total operating energy for the building for this 650 I am multiplying because it is per year, sorry not per year, per meter square, not per year, meter square, and this is this 80 I am multiplying is for the per year. So, this total embodied is the per meter square, and this is per year. So, if you do that, the total life cycle energy I can calculate, and also I can say that the 80% is the total operating energy, 6% is the total recurring energy, and the 14% is the total initial embodied energy, and by this formula the OE intensity I know how much kilowatt hour per year from the last slide. If you go back, if you see, this is that, this OE, then this is the initial embodied 11,000, this is the EEI, this 3 data I required, this data I required, and also this one is the 5500 per year, this is the ER data. So, based on that if I calculate, I can get the 15.4. So, 15.24 is, so 15.24 years the overtaking time, and finally, I can say this is the last slide. So, there can be many ways of cutting through. This is the, if the operating energy cutting almost 45 degree inclination or so, or maybe this middle funnel. So, it is a normal efficiency. If it is cutting like the above that, it is a low efficiency, it is very stiff, and if it is below the part, so it's, you can say it is a high efficiency. So, we discussed about the embodied energy, which is about 15 to 20% of the total life cycle energy, and we conclude this particular embodied energy part with this lecture, and operating energy has a major share we see, and we see the how to reduce the footprint by controlling the operation energy. Thank you very much.